Hello, and welcome to another day in AP Statistics. Today, we'll be talking about sampling distributions. In data analysis, what we as statisticians do is we are looking to find out the um, the value of something in the population. It's called a parameter. Okay, so for example, if I wanted to find the average height of American women, then I could do one of two things. I could ask every single American woman their height. However, with the population being so big, that is nearly impossible. So instead, I would take a sample from my population, collect the data, and make an inference on the population based on that sample. To do this, we are going to have to know the difference between what's called a parameter and what is called a statistic. A parameter is a number that describes a characteristic from the entire population. In my example, the parameter would be the average height of all American women. The statistic is a number that describes a characteristic of the sample. So if I took a sample of 50 American women and found that their average height was 5'5", then that means the statistic would be 5'5". Doesn't mean that the statistic and the parameter are exactly the same. It's just that the statistic represents the sample while the parameter represents the population. You can remember this with S and P. Statistics come from samples, parameters come from populations. We are going to differentiate between statistics and parameters by using different symbols. The Greek letter mu is what we use when we're talking about the average or the mean of the population. So mu, which we have been using as mean, is now going to represent the mean of a population, also known as a parameter. Whereas x bar is going to mean the sample mean, meaning the average of a sample. If we're talking about proportions, we use P to represent a population proportion. So P is a parameter, while P hat, so P with a little hat on it, represents the sample proportion, also known as a statistic. So we have mu and P are parameters, X bar and P hat are statistics. And those are universally known in a data analysis world, and we'll be using those moving forward. So when we're gathering samples, every sample could be slightly different, right? I could get a sample of 50 women and the average height is 5 feet 5 inches, but I could also get an average of another 50 women and their average height is 5'4". And I can get another 50 women and that average would be 5'6". And therefore every sample could be a little bit different. So the basic fact is called sampling variability. The value of the statistic varies in repeated random sampling. Okay, it's not always going to be the exact same value. So instead of taking one sample, what if I took many samples of the same size from the population? So what if I took many samples of size 50 and found the average of each of those samples? This would make what's called a sampling distribution. If we took every one of the possible samples of size n from a population, we calculated some sort of statistic, so a sample proportion or a mean, and graphed all those values, we would have what's called a sampling distribution. So if we took, for example, every single sample of size 50 from American women, and we found the average of each of those individual sizes of 50. And we took that average, which we call X bar, and we plotted them onto a graph or a distribution that would make a sampling distribution. Okay. In practice, it's difficult to take all of the possible samples of size n to obtain the actual sampling distribution. So instead, we're going to use simulations to imitate this process of taking many samples. Okay, so now we have three types of distributions. We have a population distribution where every single, if we think about this as dot plots, let's think about it as dot plots. Every single dot on a population distribution would represent a single individual, whatever we're measuring. So in our case, let's say we're measuring the average height. Every dot would represent a single person's height. Okay. Then, so a population distribution would be huge. The distribution of sample data is just a distribution of the single sample that we collect. For example, if I collected a random sample of 50 females, then that would mean that you would only see 50 dots in my distribution of sample data, because every dot would represent an individual, but the individual comes just from my sample. So my population distribution would have approximately 150 million dots, whereas my distribution of sample data would have just 50 dots. Then the third distribution is what we're focusing on today, and that's a sampling distribution. Every single dot in this distribution represents the average height of a random sample of 50. Okay, so every single dot is actually an X bar, whereas in number 1 and number 2, every single dot is an X value, meaning in our case a height value. Okay, so in number 1 and number 2, every dot represents an individual. In number 3, a sampling distribution, every dot represents the average height of 50 women. For example, on the left, you will see a population distribution. If I had a bag, and my bag contained 200 colored marbles, half of them were blue, half of them were red. Here is my population distribution: 100 blue marbles, 100 red marbles. My parameter, P, is 0.5, okay? Because that is the proportion of blue marbles. Actually, it's going to be red marbles, sorry. Proportion of red marbles. Then I take a simple random sample of 20 marbles, and in that simple random sample, 8 of them are red, 12 of them are blue. So now my p hat value, which is the statistic that I got, is 8 over 20, or 0.4. I took another simple random sample, and 11 of the marbles were red, and 9 of them were blue. So my p hat value here was 11 over 20. I took another simple random sample, and I had 13 red marbles, and I got 7 blue marbles. So my p hat value is a little bit different. So every p hat value is going to be a little bit different because every simple random sample has a possibility of having some sampling variability. If I did this, if I took simple random samples of 20, if I did it an infinite amount of times, if I took every possible simple random sample of size 20 from my population, and I plotted their p hat values onto a distribution, I would get this over here, which is a sampling distribution. Okay, a sampling distribution is a distribution where everything is a p hat value. Okay, so how do we describe sampling distributions? The fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator for a parameter? So how much can I trust the statistic that I gathered from my sample? To get a complete answer, we need to consider the center, the spread, and the shape. So the center, we're dealing with both bias and unbiased estimators. In our examples, in my marbles examples, they call them chips, I call them marbles. In the marble example, we collected many samples of size 20. We calculated the sample proportion of red marbles. How well does this sample proportion estimate the true proportion of red marbles, where p is actually 0.5? Okay, so we're going to note, so that you'll see that this is my sampling distribution, and you'll see that the center of my sampling distribution is very close to the true parameter, 0.5. Right? We know that 50% of the marbles are actually red, and if I took many samples of size 20, the center of my sampling distribution is 0.5. If we did that for an infinite amount of times, we would get the center is exactly 0.5. So a statistic is used to estimate a parameter as long as it's an unbiased estimator. Okay, what does that mean? Well, the way that we gather the sample has to be unbiased. It's got to be a random sample. As long as we're taking a random sample, then our statistic will be an unbiased estimator, meaning that the center of its sampling distribution will be the actual parameter. Okay, assuming that we collect the data correctly, if we were to do it many times, we would get a sampling distribution where the center is the actual parameter. What about spread? Well, obviously, the lower the variability, the better. Okay, variability is going to be it's going to depend on how large my sample sizes are. On the left in the green, you'll see a sampling distribution with a sample size of 100. On the right, you'll see a sampling distribution with a sample size of 1,000. What you'll notice is that the centers are the same. They're both 0.37. Okay, the difference is this spread is much smaller than this spread. Okay, so larger samples have a clear advantage over smaller samples. They're more likely to produce an estimate closer to the true value of the actual parameter. Because our goal in data analysis is to estimate a parameter. Parameters are usually very difficult to find, so we use sampling and sampling distributions to find or to estimate our actual parameter. Okay, like we said, the variability of a statistic is described by the spread of its sampling distribution. This spread is often determined by the size of the random sample. The larger the sample gives smaller spreads. But remember, we got to be careful about how big our sample is relative to the population. Because if we think back to our independence rule, the sample has to be at least 10 times less than the population. Or another way to put it is that the population is at least 10 times bigger than the sample, right? Because when we're sampling without replacement, we're not really taking independent random samples. So our task is to have our population be so big that each sample doesn't affect the other samples. So we still have to keep in mind our what's called our 10% rule. Okay. So here's some examples. The first bullseye is a high bias, low variability, meaning that I'm continuously hitting a spot that doesn't actually represent the parameter. Okay, think of the bullseye as the actual parameter and each dot as a sample statistic. And I continuously hit the wrong sample statistic. What does that mean? It probably means that the way that I collected my data was wrong. Okay, and I was continuously getting the wrong information. The next one, B, is low bias, high variability. Okay, that's where I was collecting good random samples, but my sample size probably wasn't large enough because I was getting a lot of variability. The bottom left is high bias and high variability. You'll see that again, I was collecting samples that weren't good because I was clearly hitting not my target, and I was also collecting small samples because I was getting a lot of high variability. And then ideally, you want very low to no bias and low variability, which is what you see in the bottom right corner. That's where I'm taking very good random samples, continuously hitting a statistic that is ideal, and my sample size is large enough where I don't have a lot of variability. Okay, bias again means that our aim is off and we're consistently missing the bullseye, and that's because the way that we're collecting something is incorrect. And high variability means that with repeated shots, we're all over the place. Usually has to deal with a small sample size. So the higher our sample size, the lower our variability will be. Okay, here's how it would look if we were looking at a distribution. You will see the first one has high bias and high variability because here is my population parameter. But if this is my sampling distribution, that means I was the center of my sampling distribution is over here. But if we have a low bias way of collecting data, our center of our sampling distribution should be our population parameter. Okay, so the first one is high bias and high variability because I'm all over the place and my center is not my population parameter. This one is perfect. Okay, this is low bias and low variability. You'll see the center of my sampling distribution is the same as my population parameter, and I'm pretty consistent in hitting the center. The next one is low bias, high variability. This is where I am kind of all over the place, but the center is still my population parameter. And the last one is high bias and low variability, where I'm consistently hitting something that's over here. That has to do with the fact that I'm doing something wrong while I'm collecting my data. Okay, let's look at this example in a different window. Here we are. Here we are identifying the population, the parameter, the population, the parameter, the sample, and the statistic. Okay, so we're finding 4 things: 1, 2, 3, and 4. Okay, so it says the Gallup poll asked a random sample of 515 U.S. adults whether or not they believed in ghosts. Of the respondents, 160 said yes. Okay, so a couple of numbers here. 515. So let's start with the population. What is the population? Well, the population is going to be the U.S. adults. All of the U.S. adults. Okay, because I asked U.S. adults about whether they believe in ghosts or not. Okay, so the sample is going to be the 515 U.S. adults that I asked. That's my sample. Then we're looking for a parameter that goes with our population and a statistic that goes with our sample. Okay. The statistic that they give us is that 116 said yes. So our statistic is not 116. Our statistic is 116 out of 515. And that is our p hat value. So if we were writing this, I would say p hat is equal to 160 over 515. This is our statistic. And we use p hat to represent a statistic. Whereas the parameter, we don't know the parameter, but the parameter we're looking for is p. We use p hat to estimate p, and then we use x bar to estimate mu. So let's just put a little chart over here. We have parameters, and we have statistics. Statistics. All right, and let's talk about different types of parameters. So we have mu, and then we have x bar. X bar estimates mu. Mu is for population, x bar is for statistics. Then we have p and p hat. This is a statistic, comes from a sample, and this is a parameter, it comes from our population. We use this to estimate this. And the other big one is going to be sigma. Sigma versus S sub x. This is standard deviation of a sample. This is standard deviation of a population. Very different. That's why in our calculators, we always look at S sub x, and we don't look at this guy, which in our calculator is sigma sub x, because this is different than this. Okay. Now let's look at our last example. During the winter months, the temperatures outside of the Starnes' cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mr. Starnes sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during a day. the minimum reading is 38 degrees. Okay, now we have a lot of things happening here. So the population is going to be all of the times in a given day at a cabin. Okay, so the population is all the times. So let's go to B. The population is all possible times. And then the sample is going to be the 20 chosen times. All right. And then we're looking for our statistic and our parameter. The statistic that they give us is the number 38 degrees. And what is that? It's the minimum reading equals 38 degrees. There's no fancy symbol for minimum reading. We just write out minimum reading. And that is a statistic because that's the coldest reading from the 20 randomly selected times in a day. So it's the coldest reading for my sample. The parameter I'm looking for is just the minimum temp in the day. So whatever the coldest temperature is during any day is what I'm looking for. Okay, again, parameters we are usually looking for, and we use statistics to help us estimate parameters. Okay, I'll see you all in section 7.2.